Greetings, everybody. We're now doing the Earth and the Moon chapter, chapter 16. This is one big important chapter. The Earth is the most important object to us, anyway, in terms of a planet. And the Earth and the Moon are so different, as you'll see. They probably don't belong in the same chapter together, but we'll go ahead and take it as it comes. This is a beautiful shot of an Apollo 17 astronaut in the lunar rover. It was an electric car, and they were able to drive around and had a million laughs at it. Let's go ahead and dive into this. Here's the 4 stages according to the text of the planet development. Number 1, differentiation. You've heard of that before. All that is core formation due to heating of the interior. When the interior gets hot enough, the heavy stuff begins to fall to the center. That means iron, and the lighter stuff, that means the rocky materials, tend to pop up like corks. And this is due to, the heating is due to accretion. Actually, since there's so many bodies coming in and hitting the Earth as it's developing, that makes it hot all by itself. Radioactive elements give off heat, planets are filled with them. And so those are 2 sources for making the interior hot. Second thing is, after the core forms, cratering becomes a big deal, because cratering is from leftover accretion. You got a lot of particles coming in and hitting, and also from asteroids and comets over a period of time coming in. Incidentally, one of the important things here I'm underlining for you, when you look at a surface on a world like the moon, when there are more craters, that means the surface is probably older. And the way they can get away with that is not much happens on the moon. So what you see is kind of what you get. And if a surface has been exposed for a long time to space, it'll have more craters than a surface that hasn't been. It's just that simple. Flooding, this refers to volcanism on the moon, Mare flooding. The Mares are the dark areas on the moon. And they're all over the front side of the moon. They're sparser on the back side. There was volcanic flooding on the Earth, and he also includes ocean flooding on the Earth as well. Slow surface evolution, that's what we've been putting up with for billions of years on both of these planets. Plate tectonics, we'll talk more about that in 2 seconds. That's when you have a very mobile surface when there are things colliding with things, and we've got volcanism and earthquakes and a lot of dynamic stuff happening. On the moon, it's mainly cratering. For the last 3.5 billion years, there hasn't been much in terms of cratering, because most of the cratering happened early in the moon's history. By the way, it's a good thing. If there were a lot of big objects coming in and hitting the moon, they'd also be hitting the Earth, which would mean you and I'd be living in caves if we were living at all. Here's the Earth's interior. This is known because of the science of seismology, which analyzes earthquake waves. And we know without any doubt that the Earth has a large iron core. There it is right there. It's more than 50% the radius of the Earth. The outer part is molten. That means it's liquid, it's hot. The inner part is frozen solid. And beyond the outer core is the lower mantle. That's all rocky material, and so is the crust and the upper mantle. Rocky material. We'll talk a little bit more in a second about subduction zones. Mid-ocean ridges are just that. They're ridges that run down the middle of the oceans, and they're big volcanic areas. Anyway, rocky mantle and crust, large iron core. Incidentally, the outer core is the location for the origin of Earth's magnetic field. There it is. Magnetic field originates in the outer core. Subduction, which is a process we'll talk about in 2 seconds, actually destroys all the ocean floor that's beyond, say, 200 million years. In fact, most of the ocean floor is younger than 125 million years. That's very young when you consider that the Earth itself as a planet is 4.6 billion years old. So there's been a lot of ocean crust that's been killed, destroyed over a long period of time. Here's plate tectonics and subduction. When you have a continental crust here, and here you have an oceanic crust, and when they do a head-on collision, see the black arrows? What happens is that the ocean crust gets shoved into the mantle. That's because it's made of heavier rock. And the continental crust acts sort of like a cork. And what happens is you get very deep earthquakes. Most of the earthquakes on the Earth are within 60 miles of the surface. These things could go down several hundred miles. That's how people began to think there was something funny happening here. The other thing that's important is that carbon dioxide is taken out of the atmosphere by the ocean on a routine basis. It gets lodged as carbonate rocks in the ocean crust. It gets subducted as well. The trick here, the really important thing, is that this material melts when it gets deep enough. It gets hot and it comes up to the surface again and is released volcanically back into the atmosphere. A lot of these carbonate rocks bring their carbon right back up to the Earth via volcanism at a subduction zone. So there is no net loss of carbon from the atmosphere due to this process. It's all actually recycled right back into the atmosphere. Long term, that's very important because that means the temperatures on the Earth don't get extremely cold. Without this process, the atmosphere would literally freeze out over a period of time. Now, talking about the atmosphere for a second, primary versus secondary. Primary would mean that we've got the same atmosphere that we had from the beginning. That's almost impossible because the origin of the moon involved a very large impact of the Earth. Roughly, we're talking a Mars-sized body came in and hit the Earth and blew material all over the place. But more from our point of view here, we're interested in the atmosphere was stripped away, and so was the water. So the atmosphere that we've had for billions of years since that time is secondary. That means it came mostly from outside, maybe a little bit from outgassing in the interior of the Earth. We'll talk about that a little bit later as well. Composition of the atmosphere right now is about 78% nitrogen, 21% oxygen, and other things involving CO2, water, and stuff like that. Now, the composition of the atmosphere is important because it has to do with the greenhouse effect. We're going to talk about that a little bit downstream. Here's the greenhouse effect. That's going to be in the next chapter when I talk about how Venus lost its oceans, we think, probably 4 billion years ago. And the Earth is getting ready to do something similar like that, but not for quite a while yet. The future of the Earth is that as the sun ages, a normal aspect of that is that the sun gets brighter. The sun, in fact, increases in brightness 10% every billion years. And so the models show, or most of the models show, that all you need is 10% brightness increase, and then the oceans will be triggered, they'll be destabilized, and they'll begin to escape. And we'll go into that next chapter in more detail. Here's the two key aspects of planets right here, friends, that you need to know about. There's only two. The first is mass. The bigger the planet, the warmer it tends to be in the core because it's better insulated. For example, the Earth has 80 times the mass of the Moon, so that means the Moon has a little over 1% of the Moon has a little over 1% of the Earth's mass. So the Moon should have very little of its original heat left, whereas we know the Earth has a lot because the central temperature of the Earth has been measured at 6,000 degrees. That's pretty hot for a world that's been cooling off for 4.5 billion years. Anyway, the volcanism on the Moon has ceased a long time ago, and you know that the Earth's central temperature is like the sun's surface temperature. That's just to give you an example of how warm it really is in there. The second key fundamental thing is solar distance. This is real easy. Planets close to the sun tend to have warmer surfaces, and interestingly, the Earth and the Moon have the same solar distance, but temperature variations on the Moon are humongous because there's no atmosphere. Okay, every 2 weeks you have daytime on the Moon, every 2 weeks you have nighttime, and the temperature fluctuations are just huge. Okay, so let's talk about the Earth a little bit. About the Moon a little bit here. The Moon has impact craters. Almost everybody who's ever seen a picture of it knows that. And that tells you the surface hasn't been really disturbed in a long time. Many areas on the Moon are greater than 4 billion years old. We know this for two reasons, because we actually had radiometric ages using radioactive elements that have actually shown us that the oldest areas on the moon are 4.6 billion years old. And also crater counting. Remember I told you that if a surface has more craters, that means it's going to be older than a surface with less. And we can actually see that there are lots of places on the moon that apparently have very ancient surfaces. If you're standing on the moon, it would be, you'd feel a gravity of only 1/6 the Earth's. That's kind of nice. That means you'd be able to jump 6 times as far on the moon as you can on the Earth. The other aspect of this, as I pointed out here, is that large impacts scatter ejecta all over the moon. Remember that large impacts throw out material? That's called ejecta. And because the gravity is so low, the bigger craters can throw things literally all over the moon. The origin of the moon happened around 4.5 billion years ago, just after the Earth originated. This is due to a Mars-sized impactor of the Earth. And what happened was it knocked off an enormous amount of Earth's mantle into space, fragmented it, and some of that material escaped from the planet, some of it fell back to the Earth, and the rest of it actually stayed in orbit and coalesced into the moon. That's the favorite theory of today. The other aspect of the moon that's extraordinary in today's terms is that there are craters near the north and south poles that are large enough so that their walls actually shadow the sun. In other words, the sun never shines into the floors of these large craters. That's partly that's the reason is because the axial tilt of the moon is very small. And so there are permanently shadowed craters near the north and south poles that have been studied for many years. And we know that they have, we strongly believe, put it that way, that they have billions of gallons of water beneath the surface. That's a lot. And so large lunar colonies would initially probably form around these arenas. NASA plans to land astronauts in the areas of these things probably in 2024 or 5. And we're actually almost done with this video. It's amazing. Secrets of the moon. I thought I'd show you how this works a little bit just for fun. If you're wondering how can people possibly know what happened on the surface just by looking at it, you actually tell quite a bit. This crater, by the way, large craters tend to be named after dead people, particularly people that had some notoriety. Archimedes, of course, a famous Greek philosopher, this is his crater. This thing is probably 85 kilometers across. Here's Aristillus. A little bit smaller. We're going to ignore Autolycus, this one here. I want to focus on these two craters. Let's look at Aristillus first. The question is, which one of these craters formed first, and what was the general sequence of events in this whole area here? And what we can actually see is 3 things. We can see the crater walls in both Archimedes and Aristillus, and we can see this general level area here, smooth area here. This is what's called a mare region, M-A-R-E. And the mares were very fluid lavas that came out they've actually been measured in terms of the ages between 3.2 and 3.5 billion years. Remember, the moon formed around 4.6 billion years ago. So that was some time after the moon actually originated. Okay, so look at Aristillus. This is a classic large crater. This thing is probably, I'm guessing now, you're looking at 30 miles across. It's big. Notice it has mountains in the center. This is formed by a large asteroid that came in and excavated this area, exploded, threw a lot of material out. It's called ejecta. The ejecta actually lands within 1 diameter around the crater. You can see it piling up here. There are what are called terraced walls in these types of craters. This is not volcanic. It's actually a rebound feature. It's like when you drop a marble into a glass of water. Try it sometime. And what will happen is the marble will initially make a crater in the water, but the water will rebound. And what happens on the moon is the rebound is actually frozen because it loses heat very rapidly. Now compare Archimedes, an even bigger crater than Aristillus, to Aristillus. One thing that's missing is, look right here. There should be an enormous ejecta blanket, and it's not there, but it is here. So the only way we can, Archimedes had an enormous ejecta blanket. A reasonable conclusion is that it was destroyed. What destroyed it? Well, what is likely to have destroyed it is the flow of this very fluid mare material out across the surface. That means that Archimedes' impact must have occurred before the Mare material did. And notice the Mare material actually seeped into Archimedes itself and destroyed most of the interior features, including these central peaks that I was telling you about before. So why did Aristillus retain its ejecta blanket? Because Aristillus came after the Mare region did, and so its survival actually was assured. So the sequence of events is clear. Archimedes' impact occurred, then the Mare material flowed across the surface also into Archimedes, and then after that episode was done, Aristillus formed on top of all of the Mare materials. That's the way this game is played sometimes when you're trying to come up with a lunar history.